So welcome to this virtual Space Connects Us event, where we connect space experts, astronauts, and leaders from all around the world with educational institutions, students, and online viewers. This event is hosted by Luxembourg's Asteroid Foundation and SnT. I would like to thank you all for joining us today. My name is Murdoch, and I'm the program manager at Asteroid Foundation. Today, we have the privilege to discover the fascinating work of Naomi Murdoch and Jean-Baptiste, researchers who are involved in the most exciting space missions. They will tell us about state-of-the-art software and hardware technologies used in planetary exploration, their link to NewSpace, and what opportunities they present for those who'd like to pursue a career in the space sector. So I would like to introduce Naomi. Naomi Murdoch is a faculty researcher at the Institut Supérieur de l'Aéronautique et de l'Espace with a PhD in physics and planetary science. She is the principal investigator of the wheelcams on board the CNES DLR MMX rover that will land on the Martian moon Phobos in 2027. She has a leadership role in the ESA-HERA mission to asteroid Didymus and is a member of the NASA DART, InSight, and Mars 2020 Perseverance sign teams. Yes, so an interesting fact about Naomi is that she has an asteroid named after her in recognition of her contributions to small body science. And another speaker today is Jean-Baptiste, who has been a co-investigator on space missions to asteroids and comets since he graduated in 2010 from the Technical University of Braunschweig. He worked at the Max Planck Institute for Solar System Research in Göttingen until he joined the DLR German Aerospace Center Institute for Planetary Research in 2016, where he has led an international working group on the origin and evolution of small bodies. He received several awards for his contributions, and he coordinates data analysis activity in ESA's HERA mission to asteroid Didymus and the Near Environment Working Group in ESA's Comet Interceptor mission to a dynamically new comet. Naomi, Jean-Baptiste, we're very happy to have you here. How are you today?
Good, thank you, and thank you for the invitation to join you.
Yeah, thanks for having us.
That's really great. Once again, thank you so much for joining and talking to the students. And talking about the students, today we're also joined by the students of the Interdisciplinary Space Masters program at the University of Luxembourg. This innovative program balances business and technology, from rocket science to the management of space businesses. These students will acquire various skills in the Luxembourg space industry sector and develop the entrepreneurial mindset required to be successful. Welcome to you all. Thank you for taking the time to join us today. And Naomi, the floor is yours.
Thank you. Okay, I'll just share my screen. Yeah. Okay, so my name is Naomi Murdoch. As Anna said, I am a researcher in the Space Systems for Planetary Applications team at ESA Interdus. And today, my goal is to give you a fast overview of some of the projects I'm involved in. And these are going to range from the very large scale of very large expensive exploration program missions to, at the end, some more perspective or some other missions that are involving more of a commercial or a new space component. So I'll try to give you some facts about the different missions as I go along and also explain my role. Obviously, I won't have time to be very detailed, but you can ask questions later on the parts that you're most interested in. Okay. So who am I? As Anna said, I'm a planetary scientist and a physicist, and I'm involved in space missions and development of space instrumentation as well. So I'm involved in different missions that range from missions to asteroids, specifically the binary asteroid Dimorphos and Didymus, to missions to Phobos, the Martian moon, and also missions to Mars, and specifically InSight in Mars 2020. So I'm actually going to talk about the latter ones in more detail today because I know that Jean-Baptiste is going to talk more about the small body missions a little bit later. So the first mission I'm going to talk about is the Mars 2020 Perseverance rover. Mars 2020 is the most advanced astrobiology laboratory ever sent to another planet. Its #1 goal is to search for ancient life. And you can see that it's a very large, complex rover here, and with many, many different instruments. And this is the SuperCam instrument that I'll talk about shortly. And down here, this is the Ingenuity helicopter. It's the first rotorcraft to be able to fly on the surface of another planetary body. So this is a big program. It's part of the NASA Mars Exploration Program mission. So their goal is to take samples with the Perseverance mission, store them, and then later there'll be the Mars sample return missions that are going to go and retrieve those samples and bring them back to Earth, all in the search for ancient life. So the development started in about 2013, and then it was launched in 2020 and landed in February 2021. And the mission is still operational today. The spacecraft was built by JPL in California, and the estimated cost of this mission, because it's a very large-scale mission, is around $3 billion, $3 billion US dollars, I believe, and that's including the launch costs. Now, as you can see, there's many instruments on board. There's the SuperCam instrument that I'll talk a little bit more about. There's the MassCam-Z instrument, which is an incredibly high-resolution imager that actually took this image that's behind me today. There's the RIMFAX, which is the ground penetrating radar. There's MOXIE, which is the technology demonstration trying to produce oxygen from Martian carbon dioxide. And then we have spectrometers as well. And finally, MEDA, which is the weather station, measuring what's happening with the wind, the temperature, the pressure, the dust in the atmosphere. So the mission that the instrument that I'm most involved in is the SuperCam instrument. So this is a bit like a Swiss Army knife of different sensors, actually. So we have 5 different types of instruments all together. First of all, there's an extremely powerful imager. It's called the RMI imager, and it's actually a telescope that's used not to look at the stars, but to look at the ground, and so can zoom in extremely high resolution and get beautiful images of the Martian ground. And then we have the LIBS instrument that uses a infrared laser beam to pulverize material on the first surface of rocks. And this actually forms a plasma, and then we can do spectrometry of that, trying to understand what is the chemical composition of those rocks. We have the green laser here. This is the Raman spectrometer. And this instrument tells us about the molecular structure, so the minerals and organics of the structure of the rocks. Then we have the visible and infrared spectrometer. And so this analyzes light from the sun that's reflected from rocks, and again allows the mineralogical composition to be determined. And then the last instrument, and one I'll talk a little bit more about afterwards, is the microphone that's also part of the SuperCam instrument. Now, all of these instruments were contributed from various different laboratories, but they all had many different collaborations. And one of the commercial ones, just to highlight here, is Thales, and they were the ones that provided the laser for this instrument, and also for the ChemCam instrument that was part of the Curiosity rover as well. So the microphone's an exciting instrument. We've designed and built it at ESA Supero, and it's the instrument that actually allowed us to record the first ever sounds coming from the surface of Mars. So it's not easy to build a microphone for Mars, because the atmosphere at the surface of the planet is very thin, which means that sounds are attenuated very strongly. So we need to have an instrument with a very high sensitivity. It needs to be able to resist cold temperatures, and also very large temperature variations, because the day-night variations can be very strong when we go to the surface of Mars. Equally, it has to survive the launch vibrations and the high levels of radiation on its journey to Mars itself. So here's a little microphone. You can see it's quite small, and the sensors is part on the end here, and then we developed the acquisition electronics at ESA Supero. And the main goals for this instrument are to study the atmosphere of Mars, to study acoustics in the Martian environment, and also to study the physical properties of rocks by listening to the laser and how it interacts with the Martian surface. So maybe a few words about my role in this mission. I was within the team that built and designed the microphone. So my role was to contribute to defining the requirements. So what do we need this microphone to be able to do if we want to listen to sound on Mars? And then I participated in instrument testing. Here was a photo of myself and 2 of my colleagues, Anthony Stornak and Jean-Baptiste, and we were testing the microphone in a wind tunnel up in Aarhus where we could recreate Martian conditions, so we could have low pressure and actually have wind flow coming through. And we were able to show that the microphone was performing well before we sent it to Mars. And then I also participate in the Mars 2020 rover operations, so helping the team to design and pilot the operations, and that involves some work with the mission team and instrument teams, and particularly on my side on the atmospheric instruments. And those are the ones that I help out with. And then, of course, there's a scientific research as well that we do with the microphone. Okay, so those were all the summary of the Mars 2020 Perseverance contributions. The team that I work in, SSPA, what we're really interested in actually is the geophysical exploration of the solar system. So we want to understand how planets and other small bodies of the solar system, how do they form, how do they evolve over time? And one of the missions that we're strongly involved in that was able to help answer that question is the InSight mission that's gone to Mars. So the InSight mission, it's a NASA discovery mission this time. It was selected in 2012, it launched in 2018, and then landed a little bit later in the same year in 2018, and it's still operating today. So the spacecraft, you can see it here in the clean rooms at Lockheed Martin, where it was built in Denver. And the estimated cost of this entire mission, I believe, is around $1 billion US dollars. And that's including all the launch costs and the operational costs and the international contributions. So there are different instruments on board. There's a seismometer used to study the internal structure of Mars, and that was produced by France. I'm going to talk about that one afterwards. There was also the mole provided by Germany that was supposed to penetrate into the ground, but unfortunately didn't manage to penetrate in very far. We have a radio science experiment, and then some auxiliary payload sensor suites, and that includes wind, temperature, pressure, and a magnetometer as well. And then, of course, we have some cameras equally on board. So this is the InSight mission. If you see on the left here, this is it being deployed, the seismometer being deployed. So first of all, the seismometer was put down, and then it was covered with this wind and thermal shield that actually protects the seismometer from the Martian environment. Seismometers are incredibly sensitive instruments. And so when the wind blows or when there's too large thermal fluctuations, it generates a lot of noise on the instrument. And when there's noise on the instrument, that stops us actually being able to hear the Marsquakes, feel the Marsquakes, and do the science that we want to do. So this whole installation was very important. Now, if we look inside the seismometer, this is what you've got. This is a sketch on the right-hand side here. Right in the middle, you've got these broadband seismometers, and they were provided by France. They were developed with the IPGP lab in Paris and a commercial partner, Southern, under the leadership of NES. And so up, if I go on, after that, we've also got a second set of sensors. These are the short period sensors in here, and they are provided by the UK Imperial College and Oxford University. So these two types of sensors, they work well together. So we've got one that's looking at the low frequencies, the very broadband seismometer, and then the short period seismometer, which is pushing up towards the higher frequencies. Then it's really important that this instrument is leveled correctly with respect to the gravitational field. So we have a leveling mechanism here that was provided by the Max Planck Institute for Solar System Research in Germany. Then we have this wind and thermal shield that I was talking about. That was provided by JPL, as was the tether here, which actually connects the instrument to the lander body, and that's where all the data and the power travels down. And then we have the electronics box. Now, the electronics box is actually in the main lander itself, and that was provided by ETH Zurich in Switzerland. So it's quite a complex instrument. There's lots of different parts to it, and there was definitely lots of interactions between the different countries and these different institutions trying to pull this instrument together and get it ready for launch. So what was my role in the mission? Well, again, I was helping out with determining the requirements for this instrument. So what do we need to do to design this instrument in order to minimize the noise on the instrument and maximize the science that we can do? And part of that was developing the noise model of the instrument. So that means trying to develop a model to understand when the wind blows, how much of a signal are we going to see on the seismometer, or when we have certain thermal variations. What is this going to do in terms of thermal noise or thermoelastic noise? And try to quantify all these different contributions to the noise in order to help with the design of the instrument and also the installation later. And that was part of the instrument deployment and the site selection as well after landing. Then this is me in the clean room at Kness as well. This is the size before launch. So it's inclined because the gravity on Mars is 1/3 of the gravity on Earth. And so in order for the sensors to work correctly, we have to incline it so that they see the same gravity. And that's why it's tilted over here. And so doing the performance test was very important because we wanted to make sure, of course, that the sensors were functioning as perfectly as possible before we send them to Mars. And then I'm now part of the team that is doing the scientific research. So I can talk more about the science later if anyone's interested, and we can talk about that. Okay, so those were the two big missions. And now maybe just a few words about some of the future missions that are ongoing, specifically linked to geophysical exploration of the solar system. So one that's coming up that's due for launch in 2024 is the Farside Seismic Suite. Now, this is an interesting mission because it's actually part of the NASA Commercial Lunar Payload Services Initiative. So that means it's commercial companies that are going to be delivering science and technology to the lunar surface. And so we were contributing, Isao Supero is a scientific and technical partner of the Farside Seismic Suite that is being taken to the surface by Draper here. And this is a schematic of the lander on the far side. And so it's an interesting program. There's going to be quite a lot of different opportunities for commercial initiatives there, ranging from payload integration and operations, launching and also landing on the surface of the moon. Another mission that I love very much is the Dragonfly mission. This mission is going to go to Titan. It's a Johns Hopkins University APL-led NASA New Frontiers mission that is scheduled for launch in 2027. It has several commercial partners, including Lockheed Martin and Honeywell Robotics. And the idea here is that it's going to be a rotorcraft aircraft that's going to land on the surface of Titan and then be able to fly to different locations around the surface. And at these different locations, it's going to make various measurements. And some of those measurements involve a seismometer that will be deployed to the surface in order to study the subsurface of Titan. And then another one that's still at the mission concept phase right now is the exploration of the subsurface of Venus, but from using measurements in the atmosphere of Venus. So this is a JPL-led mission concept, but it involves IPGP and one of my colleagues, several of my colleagues at Isao Supero. And it's Rafael Garcia that's leading that effort for us. And so the idea is that when there's a quake on the surface of Venus, when the ground moves, this actually creates a pressure wave that then moves up into the high atmosphere. And so if you have pressure sensors in the atmosphere, you can see that pressure wave coming past, and you can use that to try to understand how big an amplitude that quake was at the surface, and then subsequently interpret the internal structure of Mars. And this is a really fun mission concept because it avoids that constraint of having having a long-lived seismic station or any kind of lander at the surface of Venus because of the very hostile environment. So we can do seismometry from the atmosphere. That's going to be a massive and very exciting advancement for seismology. And then just to finish, a couple of words about small bodies and asteroids as well. So understanding the internal structure of asteroids is really important for science, for planetary defense, and for in situ resource utilization. And most asteroid mining companies now generally agree that a prospecting spacecraft is going to be absolutely necessary for mission success for any kind of resource extraction mission. And radar and seismometers may prove to be the instruments that are used for future prospecting activities. So in this image here, this is a picture of the Juventus CubeSat. It's on the Hera mission that's going to be going to the asteroid Didymos that I think Jean-Baptiste is going to talk about just afterwards. And this was provided by NewSpace, this CubeSat. And these antennae that you can see coming out, these are the antennae from the radar. And the radar, you can see the electronics box in the bottom left here. It's a low frequency radar that was developed for Hera, and it was built by several different partners. So in black here, we have the academic institutions. University of Grenoble-Alpes is the one in France that's leading this development. And then we have industrial partners too that are providing different parts of the instrument, including Mtronics in Luxembourg. Then another thing that we're developing in-house at ESAI Superior are two different new compact seismometers for small bodies. And so these are hopefully going to be included in future space missions. And the one on the right here, Pioneers, is being built in collaboration with XBlue in Paris. And these are actually both funded through a European Commission Horizon 2020 projects currently. Okay, so I hope I've been able to give you a bit of an overview of the different activities I'm involved in and where NewSpace might come in and play a role. As we go forward, I think the message I wanted to make was that the really big science missions are still largely institution driven, but the commercial space sector is providing a larger and larger role in planetary exploration. And the types of roles that they play include things like the launch vehicles, the spacecraft platforms, technical equipment, payloads and payloads integration, and also as we go forward in the future, perhaps things like resource extraction as well. So we'll see. And I think Jean-Baptiste is going to talk shortly about the some of the software side of things as well, that's really important for all of these space missions and exploration missions. So I'm going to stop there. Thank you very much for your attention, and I look forward to having some questions from you after Jean-Baptiste.
Thank you very much, Naomi, for your presentation. So exciting. And honestly, I should say that it's also great to see that Luxembourgish companies are involved in all these exciting activities. So thank you once again so much. And now over to Jean-Baptiste.
Thanks, Anna, and thanks, Naomi. I'm going to share my screen now. Okay, you should be seeing my presentation. So, hi, everyone. As Anna introduced me earlier, my name is Jean-Baptiste Vincent. I'm a researcher at the Institute of Planetary Research in Berlin, in Germany. And this institute is part of DLR, so the German Space Agency. And we have been involved with space missions to almost every object in the solar system since many, many decades. And today I'm going to tell you a few things about the state-of-the-art instrumentation for planetary exploration, but particularly in the context of mission to small bodies, so asteroids and comets. And I must admit, when I was preparing this talk, at the beginning, I was not so sure about what I was going to tell you in 10 minutes, because this is such a vast subject with many things that we could discuss. So I tried to remember my state of mind when I was a master student, and I realized that at that time, I was unaware of many jobs or many tasks that are related to a space mission that go perhaps beyond what you think of when you are thinking about engineering or about science. And I will mention these in the coming slides. So first, I will tell you a little bit more about myself. So I had the privilege to be involved in many space missions since I graduated. And they are listed here. So I've been working with missions for the European Space Agency, like Rosetta, or currently the Hera mission and the Comet Interceptor mission. I've also worked with NASA on the Dawn mission that visited asteroids Vesta and Ceres, which are among the largest asteroids in the solar system. And the DART mission that just collided with one of the smallest asteroids that we know, asteroid Dimorphos. And I've also been working with JAXA on the Hayabusa 2 mission, part lander that landed on asteroid Ryugu a couple of years ago. And I have had different roles in these missions, from scientific investigator to a more leading position in different groups. So for instance, for Rosetta, I was in charge of the science planning and operations planning for the scientific camera on the mission. So it was 2 years of planning all of the observations that we wanted to take with the camera. Currently, I'm the principal investigator for the camera that will fly on the HERA mission, which is a European mission that will investigate what is the state of asteroid Didymos and Dimorphos after NASA has crashed a spacecraft onto the smaller asteroid a couple of weeks ago. So thanks to all these missions, I had the opportunity to be really on the front seat to investigate a huge amount of different types of asteroids and comets, different shapes, different composition, different sizes, going from very small objects that are a few hundred meters in size to objects 1,000 kilometers in size, like Ceres. And all these small bodies, these asteroids and comets, they are really important for us because we believe they are the leftover from the formation of the solar system. And by investigating them, we learn about our own origins. We learn about how these objects were formed and how they came together to create planets. And we also learn how they sometimes crash into planets. And this can be a bad thing if we have living beings on the planet like us. An asteroid could destroy our civilization. And that's something we try to prevent with missions like DART or HERA. And that's part of the planetary defense side of my work. But there is also a positive aspect, is that we think that maybe these small bodies are the objects that seeded our planet with life by bringing to Earth some of the elemental molecules, organic molecules that are needed to develop more complex molecules like amino acids or proteins that eventually lead to forms of life like ours. And so that's something we try to investigate. But to do this, we need space missions. And this means we need to design missions with an engineering team that are going to address the scientific questions that we pose. And often when you think about this, you may think that these are two separate worlds. On one side, we have the engineering that is just building the spacecraft and the instruments. And on the other side, you have the scientists who will investigate the data and publish some results. But in reality, when you start working in space missions, you realize that everything is really interconnected. And there are lots of different topics and different jobs that are at the border between engineering and science. And that's something you will get involved with, whether you continue your career in a more engineering side or in a more scientific side. You will have to deal with both parts of the project. And here are some examples. So let's say you are going to design a new instrument and you are, I don't know, an electronics engineer, and you design some specific parts of the components that will be part of the instrument. But this instrument is designed to answer specific scientific questions. And the scientists, they have some specific requirements about the accuracy of the data they need or the type of conditions in which they want to observe. And you have to make sure that these things go well together. On the other side, the scientists, they may want to acquire a lot of data with very specific conditions because they have all these great science questions that need to be answered, but they may not be aware that not everything is possible because there are some operational constraints on the spacecraft that needs a certain amount of power, that has a limited data volume available in its memory, that needs to operate in a certain range of temperatures, that will make acquiring some of the data difficult. So there is constantly a dialogue between the different groups in order to make the best of this mission. So from instrument design to mission control to navigation, calibration, data processing, all these different boxes that I have put here on the slide, you can imagine that there are many different types of jobs that are related to that. And there is no clear path to one or the other. So when you start in a space mission, you might end up doing more of one thing or more of the other, depending on what you're currently doing for the mission. And for instance, now Naomi and I, we are both researchers that are very involved with the HERA mission, but at the moment we are doing a lot of science planning and we have a lot of discussions with the mission control or navigation people to make sure that the mission will be able to get the data that we need for our science later in the future. And to tell you more about the specific challenges that we face with this type of missions to asteroids and comets, when you go to visit a planet, you kind of have an idea of where the planet is in the solar system and what is its shape and so on. When you go to an asteroid or a comet, you have many more unknowns. Usually we kind of know the trajectory, the orbit, but we don't know the size, we don't know the shape, we don't know the gravity, we don't know what the surface texture looks like. Often we also don't know the composition. But we need to fly around there. We need to design instruments that will be able to operate in this unknown environment. We have to navigate around the asteroid and comet. We have to be able to land on the asteroid and comet safely. And these are really very difficult things to do when you have an unknown environment. So it requires a lot of flexibility on the instrument design and on the planning side of things. And often this means that the spacecraft has to be as autonomous as possible. Typically, it is preloaded with sequences of operations that can be executed without human interaction. But now, as we move to better and better spacecraft, we start to incorporate decision trees and onboard intelligence so that the spacecraft can react by itself and decide on what is the best thing to do at a special time, depending on the conditions. And all of this needs to happen fast. We need really fast reactivity from the spacecraft. And to give you some example from recent missions, on the left side, you have some of the final images from the DART mission. And the DART mission impacted an asteroid at 6 kilometers per second. And at this velocity, far from the Earth, you don't have time to drive the spacecraft. You cannot communicate fast enough. So the spacecraft had the onboard system to automatically track the asteroid and adjust the course of the spacecraft in order to hit the asteroid right where they wanted to hit it. And there was also another system that would just, instead of sending back the full image, because there wasn't much time to process the data and send back everything to Earth, the spacecraft was automatically, or the camera was selecting the part of the image that was the most relevant and only sending back this specific section of the image to save on the data volume. And these kind of things are being developed more and more. And on the right, I'm showing you now an example for the HERA mission, where we work a lot with industrial partners like GMV, who are responsible for the navigation of the spacecraft. And they are developing algorithms that can go beyond just tracking an object in the image. They are actually tracking surface features on the asteroid with the onboard camera and the onboard computer. And they use this to constantly monitor where the spacecraft is with respect to the asteroid. And with that, they can have an autonomous navigation in the system, Didymos Dimorphos, looking at the main asteroid or looking at its small moon that we are going to see in the image now in a couple of seconds. And this allows the spacecraft to react to the situation and to decide maybe to adjust its trajectory without having to refer back to the Earth and wait for instructions. And that's something that will be very important in future commercial applications, like if you are thinking about asteroids, you need autonomous navigation. So I said before, you also need fast reactivity. And that's particularly true for missions that are doing a flyby, so for a first visit to an object, because encounters in space are very fast. I told you before about the DART mission that imaged the Didymos system at 6 kilometers per second. That's not fast compared to previous missions. So there have been encounters in space up to 70 kilometers per second. And one mission I'm involved with, Comet Interceptor, that will cross the orbit of a comet or maybe an interstellar object in 2030s, will intercept the comet at 30 to 70 kilometers per second. So this is extremely fast, and you have only very little time to acquire the data that you need for the science. So to achieve that, these missions, they need to develop not only smart decision-taking algorithms that are able to make the best out of this very limited time to acquire the data, but we also need to develop new generation of electronics that allow more instruments to be able to operate in such conditions. So not only cameras, but also spectrometers or other type of instruments that in their previous versions would have needed a lot of time. Now there are new developments that make these instruments able to operate much faster. So for instance, all the CCDs on the detectors are being replaced by CMOS sensors that are faster and offer a better dynamic range to observe asteroids and comets. We see also a big update in the speed of processors. There are new designs that go from a few 100 megahertz, that's what we use now, to gigahertz. So we are not yet at the level of what you have on your smartphone or what you have on your computer, but computers that fly in space are becoming more and more capable, which means we are now starting to think about integrating full artificial intelligence like you would have on a self-driving car in order to make the most out of the missions and have the spacecraft that are fully responsive and able to take the right decisions in unknown situations. And so these are the main messages I wanted to tell you today. If you want to continue a career in space science and maybe more on the commercial side of things or on the industrial side of things, there are a lot of different jobs at this boundary between pure engineering and pure science. So in between, there are so many things to do to make a mission. And in terms of instruments, we see a lot of development in the software to incorporate more smart features to enable the spacecraft to take decisions. But we also see a lot of development into electronics to have chips that are faster, better, that use less power, and that are overall much more efficient and much smaller. Because of course, we want to develop more missions, and this means there will be probably less of these giant big spacecrafts that we have in the past, but in the future, we have many more missions that are a collection of small spacecraft like CubeSats that can investigate an object with each spacecraft having its own role in the mission. And for that, we need to miniaturize components. So that's the kind of overview I wanted to give you today. And now if you have specific questions about asteroids, comets, or space missions, I'm ready to answer.
Thank you so much, Jean-Baptiste, for your presentation. It's exciting to hear that there are so many opportunities for those who are interested to pursue their career in the space sector. So now let's go for the questions. Please don't hesitate to raise your hand. Yes, I can see a hand risen.
Hello, hi, Naomi and Jean. Thank you for the presentations. My question is to Jean regarding the Comet Interceptor missions and other missions which you said which can potentially reach up to 70 kilometers per second of delta V. I assume that there will be a lot of gravity assist to reach that velocity, but how do you slow down at the rendezvous? Do you also use gravity assist or onboard propellant for that, for 70 kilometers?
So thank you. This is a very good question. So the velocity is the relative velocity between the spacecraft and the target. And in the case of a mission like Comet Interceptor, most of the velocity actually comes from the target itself. So these comets or interstellar objects, they come into the solar system at very high speed. So the spacecraft itself will not travel very fast. It doesn't need a lot of gravity assist. It's the comet that is going super fast to the inner solar system. So we only need to be able to reach the right place when the comet is going to cross the ecliptic plane of the solar system. And unfortunately, this also means that for such a comet, we cannot really rendezvous. We will only fly by, or technically the comet is flying by spacecraft and then disappears. So we cannot stay with the comet for a long time. So everything will happen in a very short time scale.
Thank you for your answer, Jean-Baptiste. Let's see if there are any other questions. Please don't hesitate to raise your hand. Well, in the meantime, if anyone comes up with a question, I will ask one, and my question is to both of you, Jean-Baptiste and Naomi. What is your most memorable moment related to space missions? What was the most exciting, emotional, or something that you discovered that you completely didn't expect?
For me, I would say it was the first images of Comet 67P. So the target of the Rosetta mission, because we didn't know what was the shape of the comet. We had only very limited information. And we arrived there in August 2014, sorry. And suddenly we saw this crazy world that was bilobate, that had a morphology that was more complex than anything we had seen before on comets, because we never had images with such high resolution. And so this was a wow moment for me. It was really impressive. And then the following moment was, okay, now that we see that, how are we going to map this object, create a shape model, and land on the comet 3 months later? So we had really intense 3 months of work in order to make this happen, but it worked out in the end.
On my side, I guess there are two events that came to mind when you said that. The first one was the InSight landing, because I'd been working on the project for for about 6 years, and it was the first space mission that I was really involved in. And I was at JPL at NASA for the landing with the team that we were all there, the science team, and I was there because I was going to be part of the team that was choosing, once we landed, where we were going to deploy the different instruments. And so being there at NASA with during the landing with the science team, and seeing those first images coming back from the surface of Mars, that was really special. And then the second event for me would probably be, again, Mars, is the first ever sounds that were recorded at the surface of Mars. So like I mentioned during the talk, we made the SuperCam microphone. It was the first ever microphone to function at the surface of Mars. And we turned it on a couple of days after Perseverance landed. And by the time when the data came back down, it was February in 2020, I believe, yeah. And we're, no, 22, I can't even remember now, 2020. And it was the middle of the night when the data came back down, and I was at home in my cold office, and I had colleagues as well that were in different places. We're all in different places. And that first sound came down. I was listening in the middle of the night to it, and it just gave me shivers. And to this day, every time I'd listen to that first recording, I still have shivers thinking that this was the first ever recorded sounds from another planet, well, from Mars, that were being sent back to Earth. And I was listening to them in my house in Toulouse. And it was quite something.
That must have been so exciting. And wasn't it a scary sound? Because I imagine that it doesn't resemble anything that we hear on Earth.
It does actually, because the dominant sound on the surface of Mars is the wind. And so it's a bit like, you know, if you're speaking on the phone and you actually try to cover up the microphone because it adds too much noise, it's that sound that we study. And we actually do atmospheric science listening to that sound, and we can do a lot of atmospheric science with it. So it's just this, you know, low frequency rumble, this wind that you can hear, but there's just something extra special knowing that it's recorded in another planetary world.
I can imagine. Thank you very much, Jean-Baptiste and Naomi, for answering this question. And space is extremely exciting. And I think that anyone who is involved in the space sector can always find something breakthrough, something so new, and being there the first one to experience it. So yeah, let's see if we have any other questions in the meantime. Yes, please go ahead.
Hello. Yes, thank you. My question is again for John regarding are there any projects happening in ESA or DLR for exploring temporarily captured orbits of asteroids, like temporarily captured in geocentric orbits?
Not that I am aware of with ESA and DLR, and I don't know if there are actually objects that would be temporarily captured in a geostationary orbit. I think the Chinese Space Agency has a plan to visit a small asteroid that is a temporary companion of the Earth, so that is flying on an orbit that is almost similar to the orbit of the Earth. But I'm not aware of any other project in Europe or with the US.
Yeah, thank you very much for your answer, Jean-Baptiste. Let's see if there are any other questions. Okay, so, well, I think that now our event is coming to its end. And I would really like to thank you again, Naomi and Jean-Baptiste, for joining us today. It was such a pleasure speaking with you and learning more about the state-of-the-art instrumentation for planetary exploration and how it is linked to the NewSpace, and about all these exciting opportunities for those who would like to pursue a space sector-related career. And I would also like to thank everyone who has joined us today. Thank you so much for your attention, and we're looking forward to seeing you at our future virtual and in-person events. Thank you so much.
Thank you for having us.
Thank
Bye,
you.
everyone.
Bye.
Thank you. Bye.